Got myself a whistle. I like to blow things up today. I had a wooden whistle once, but it wouldn't whistle. And then I got a steel whistle, but it still wouldn't whistle. There's one more. And then I got a lead whistle, but it still wouldn't let me whistle. Alright, I blew it. I get it. I totally blew it. You know how flowers blow whistles, right? With two lips. Two lips. Alright, stop. Are you entertained? I hope you're entertained. Here we go. So this is directly from your homework number 4. I would briefly go over this in class to reference the problem with this and what we're about to deal with. So, what are we dealing with? Well, this is a u substitution. I know it's a u substitution because the derivative of something squared is something to the first power. So I can zip through this, and this is right off your homework, so I'm not going to spend a ton of time with this, but there's your du, 8x dx, and we need it to be 3. So we multiply by 3/8. I'm going to skip the next step and jump right to the substitution. So we've got 3/8 in front, and we'll have 1 over u du. So we end up with 3/8 ln of u, which is 4x squared plus 2. And now you can see I'm already skipping some steps and kind of jumping right to the end of my antiderivative. And I went through that very quickly because you guys already finished this problem on your homework and you already have the answer to it. So you already knew this was the solution. But I'm bringing this up for a point of emphasis. So recognize the relationship here, and now notice the problem in this integral. One little teeny tiny change, and we have a massive problem. This is no longer the derivative of this. The derivative of something squared is not a constant. So now we're left to wonder, what do we do now? Well, there is an antiderivative rule that looks kind of similar to this, but it doesn't yet. So I'm going to perform some algebra and make it look more familiar to you. I'm going to take this 3 out. Perfectly legal for me to do that. And now I've got 1 over 4x squared plus 2. Now I'm going to take a 2 out of the bottom, which would be like pulling out a half. And now I've got 3 halves. I'm going to write this in a different order, which is perfectly legal. And I end up with 1. This is now a 1 plus this is now 2x squared dx. That should look really familiar to you. This is almost what? It's almost 1 over 1 plus x squared. And that's what? That's the derivative of the inverse tangent. So this is an inverse tangent derivative. If you see addition with an x squared, a quantity squared in the bottom, you're looking at an inverse tangent. It just doesn't look like it's supposed to yet, so we have to make it look like that. How can we get this to look like that? Well, I did the 2 easy steps for you. The 3 goes out, no problem. The 2 coming out of the bottom, that's no problem. And now the last step we need, I don't want 2x squared. What I need is something squared. I need one thing, quantity, squared. So I have to do one more step of algebra. I'm going to rewrite the exact same integral, but I need 1 over 1 plus something squared. Well, obviously x times x is x squared. What times what gives me 2? What times what gives me 2? Radical 2. The square root of 2 squares to give me regular 2. And now this is a perfect fit for the inverse tangent. 1 over 1 plus something squared dx. Now this fits the inverse tangent mold. Now we can actually antiderive. So now I can actually antiderive this. This is still a u substitution. All inverse tangent problems are u substitutions. Where's our u going to come from? Your u is always going to be this little piece. Because if I took a derivative of this piece is going to come out. So in this case, my u is going to equal what's inside that squared bracket, radical 2 times x. So then du equals just radical 2 dx. And you always, 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 always need this to be 1. It has to be 1. So this will always have to go away. Every time you're doing an inverse tangent, this can't be here. Well, if this was a 2, I'd multiply by 1 over 2. If this was a 5, I'd multiply by 1 over 5. This is a radical 2, so I need to multiply by 1 over radical 2 du. That cancels this and makes it 1 dx, and now we can perform a u substitution. I'm going to replace this in my integral. The 3/2 is still coming along for the ride. And now what's going to, oops, sorry. I need this piece of information to come out front. So times 1 over radical 2 times the antiderivative of. That's being replaced with u. This is now du. And we have 1 over 1 plus u squared du. So this is the only little tricky piece, is getting this guy out of your antiderivative. Now that we've done that, it's a quick little cleanup, no need to rationalize or any of that garbage you guys didn't pre-calc. I know the antiderivative of this is inverse tangent, so I get 3 over 2 radical 2 inverse tangent of u plus c. And what was the u? It was radical 2x. So our final answer is 3 over 2 radical 2 inverse tangent of radical 2x plus c. There is our antiderivative. Notice most of the work being done here had to do with algebra. Algebra, 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 figuring out what that piece was, u substitution setup, substitute, and then we actually performed a step of calculus. Derivative was calculus, the one step of antideriving was calculus. So your goal, once you realize that your basic u substitution fails, you need to try to make it look like an inverse tangent. If this is a subtraction sign, forget about it. Game over, can't make it look like inverse tangent. Because as soon as you factor a negative out of one number, you're going to make the other number negative. And you can't make it work. If this is subtraction, that requires another entirely different anti-differentiation strategy. So let's try another one, shall we? We'll go a little bit quicker this time. So I'm going to pull out the two things I need to right away. Pull out the 5, pull out the 2. What am I left with? 1 over, rearrange it, 1 plus, it'll be 3 x squared dx. And now I rewrite this piece. So I'm going to recopy, and I want 1 over 1 plus something squared dx. Certainly x times x is x squared, and radical 3 times radical 3 is 3. So here's our setup, algebra, algebra. Now we do the calculus. This is addition, so we're ready to roll with some inverse tangent. U will always be the piece inside the parentheses if we're doing inverse tangent. So certainly du is going to be just this, and we don't want that, so we need to cancel it with a reciprocal. So I end up with this equals 1 dx, And now I can pull off my substitution. So I end up with 5/2 times this goes out front. To cancel it, we have not taken an antiderivative yet. 1 over 1 plus u squared du. And now I'll do the last two steps in one leap. So 5 over 2 radical 3. I know this is the inverse tangent of u, and u is right there. So radical 3x plus c. There we go. On a roll. Don't blow the whistle on me, all right? Couple down, a few to go. So don't forget about these guys, but remember what we focus on. Obviously, if I can give you an inverse tangent antiderivative, I could give you an inverse cotangent, but then wouldn't you just pull the -1 out front and do an inverse tangent? So let's focus on this guy right here, and you will see this guy sneak into a few antiderivatives also. Would not worry about this or this. You will see these never. And again, if I'm going to give you an inverse sine, then why mess with inverse cosine? Just pull the -1 out front and deal with a negative sign. Alright, so keep these two rules in mind, especially this one. And here are a few more inverse tangents. This one is, an inverse sine and an inverse tangent. So I want you guys to pause the video, try each one of these at home. This one I'm just going to jump to the answer on, and then the second one I will talk through and explain how we're going to use the inverse tangent. 3, 2, 1, pause. Alright, so I put up my work, skipped a couple of steps because this is now the third time we've been through this, but there's your u. I pulled out 4/8, but that simplifies to 1/2. So I made this much cleaner. There's my substitution step, and then boom, I'm done. This time I did a derivative to check. Coefficient tagged along. The derivative of the inverse tangent is 1 over 1 plus that thing squared times the derivative of the inside, which is radical 2. These radical 2's cancel. This squared is 2x squared, and then I distributed this 2 through. 2 plus 4x squared, and I got this answer, which is not that, but I can multiply this by 4 over 4, which is really 1, and I get 4, 8, and 16. It's the same thing. I could multiply it by any version of 1, and it would be equivalent. So what about that inverse sine? Well, here's the rule for inverse sine. 1 over the square root of 1 minus something squared. So we need to rewrite it such that we have this 1 minus something squared dx, and this is going to work the same way the inverse tangent does. Our something in this case I think is pretty clearly 9x. 9x times 9x is 81x squared. So now, just like with inverse tangent, our u becomes that 9x, our du becomes 9dx, which we don't want. So we simplify that out. We want 1/9 du equals 1 dx, because that's what we have on top, is 1 dx. Pull off your substitution, 1/9 in front of the integral, and we end up with 1 over 1 minus u squared, which is an exact fit, du, which is an exact fit of the inverse sine. So we end up with 1/9 inverse sine of u, which I'll plug in right away as 9x plus c. And there is a very quick and simple inverse sine antiderivative. So once you try enough of these, you start to get a little bit more comfortable, feel a little bit better about what you're doing. So I have a bunch more to practice. You don't need to do any of them. You can do all of them. It's entirely up to you. If you're getting it, you got it already, move on. But they're not down here. They're on the next slide, aren't they? Here are a bunch more inverse tangents. How do I know? Addition sign, x squared constant. addition sign, x squared constant, same thing. This one, well there's that square root, this must be an inverse sine, and there's another addition sign, x squared constant. So 4 inverse tangents and an inverse sine. So I'm going to go through them, I'll show my work, and I'll put up my answers. I'll fast forward the video to that point so you're not just watching me do these calc problems, and if you guys have questions, you let me know. So pause the video, 3, 2, 1. Alright, welcome back. Put up some of my work and my answers here. Inverse tangent, inverse tangent, inverse tangent. You see this one's really nice. Didn't have to worry about a radical, just had to worry about getting rid of the 3. This one we had radicals in. Again, this one was really nice because when I pull the 3 out, I end up with a 4x squared, and that has a perfect square root, so there we go. That one worked out nice. Inverse sine, I also made this one really convenient because this breaks down into a perfect square, no radical necessary. And then this one is a little nasty. I kind of tricked you on this one. I did it intentionally. If you pull a 7 out of this, this goes down to 7x squared. And so you need a root 7 here. This is enticing. You want to make it 7x squared right away, but then you lose your inverse trig. So you have to be really careful when you pull this 7 out. This has to be a 1, so don't be fooled by this really convenient number that looked like it was going to be nice. So there are your remaining answers. So just for extra practice, what I did is I threw these on the video also. Again, I tried to make these look like they were all the same, so that it would be very, very difficult trying to mix in these ArcTans with the U-subs, with the basic rules. You can skip them and not do any of them. You can do all of them. But again, I'm going to go through them, and I want you guys to notice the very, very subtle differences between these 4 things. So I'll have you guys pause the video in a few seconds, and then come back and look at my answers and kind of talk about, well, what's different? How do I know which strategy I'm using? Because Mr. Young, they all look the same. Well, that's the idea. They are all going to look the same. You have to notice the one teeny tiny difference that makes them require a different strategy. All right, so pause the video, and then when you guys come back, I'll have the answers up and we'll talk about it. All right, so I put up my answers to all 4, and I wrote myself a note. So what should you notice? X squared, x to the first. 1 degree away, the derivative of this is right there, this is a u sub. The second one, these are separated by addition sign. This 2 means nothing. Bring the 2 out front, and these are just basic rules. I don't need any fancy strategy for this. The antiderivative of 3x squared is x to the third. The antiderivative of 1 with respect to x is x. And then don't forget about that guy you removed. Tack along the half, and you're done. Very simple, very quick. Addition signs are great. Number 3, I've got an addition sign, x squared, and a constant. That's an arctangent. Definitely can't pull off a standard u sub. This is a unique arctangent u sub there. There's your answer. And then in number 4, don't be fooled by the exponent because this quantity is 1 degree away from this. The derivative of 2x is a constant. The derivative of that is right there. This is a u sub. I pull off the u sub, this is not an ln. That's an ln. 1 over u to the first. 1 over u to the second is a power rule. Becomes -1 u to the first. That's where the negative sign comes from. Yes, you can distribute the bottom if you want to, and write it like that if you must. I don't care if you do. So 4 very confusing integrals. Very simple if they were on their own, but putting them all on the same screen, this can become a nightmare. Alright, so you guys should have a good background with the inverse tangent. The next lesson has to do with integration by parts, which is why your homework is called this. The parts strategy is very simple, but it does take a lot of work. Once you guys understand the rule behind it, you guys will zip through it. And the second parts lesson is really, really simple. It makes it go by really, really fast. So these are still due to Google Classroom the same times they would be if you guys were in person. Let me know if you guys need help, and I'll see you on the flip side.